Hello friends, welcome back to this online lecture series on earthquake resistant design of structures. Now, in the previous lecture series, we have been discussing regarding some of the important earthquake features that with the help of introduction of these features in the building, the performance of the building can be enhanced under the effect of lateral loads. From this lecture onwards, we are going to start one very important discussion that is regarding the provisions of Indian standard IS 1893, that is regarding the design and design criteria for earthquake resistant design of structures, right? So the focus in today's lecture is going to be about the seismic zone in which the entire country is divided. Then we are going to talk about the applications of IS 1893, that is on which kind of structures the codal provisions of IS 1893 is going to be applicable. Then we are going to talk about the certain other basic parameters such as the zone factor, then importance factor, then how to calculate the horizontal acceleration, the criteria for calculation of vertical acceleration, and also certain criteria or certain assumptions that are made while considering the provisions for this particular topic, that is the codal provisions that are suggested by the Indian standard. So let us start today's session, where first we'll be starting with the discussion of the code, right? Now, as we have already discussed several times in the initial lectures regarding the philosophy that the Indian Standard Code is based, that is, it is basically talking about three types of earthquake, that is the minor earthquake, the moderate earthquake, and the strong earthquake. And in all these three types, that is, if you quickly revise, then it is saying that in case of minor earthquake, no structural damage should take place, non-structural damage should also be minimal. In case of moderate earthquake, it is said that non-structural damage should take place, structural damage should be minimum. And in case of strong earthquake, it is telling that the structural damage should be there, and structural damage can be up to the level of irreparable damage also, but in no case the structure should collapse, right? So basically the fundamental of the Indian code is that under no circumstances the attempt should be made that the structure should be collapsed. And we have also discussed regarding two basic types of earthquake that the code is talking about, that is the maximum design earthquake and the considered earthquake, right? And we have seen that if you go for the maximum considered earthquake, then in that case what is going to happen is that the structures are going to be uneconomical in nature, as the probability of these earthquakes are going to be very less. However, what we have done is that we have applied a factor and we have reduced the actual value of the maximum considered earthquake, and we are designing our structures for that particular value, so that what is going to happen is that the structures are going to be economical in nature also, and at the same time they become resistant also in nature, because the philosophy of the code is telling that we are not going to have earthquake proof structures. It is not possible to have earthquake proof structures, but the possibility of earthquake resistant structure is there, and that is what our goal as a structure engineer should be, right? So whenever any design aspect or any design project that you are going to have, then you need to finalize the earthquake parameters based on IS 1893, which you need to introduce in that particular model that you are going to make, whether it is in STAD or whether it is in ETABS. And the first question comes is regarding the location of the project or the location of the site where this particular project is proposed. So the Indian Standard Code initially has divided the entire seismic zone, seismic map of India, as you can see over here, was initially divided into 5 zones, that is zone 1, 2, 3, 4, and 5, right? But later on, after studying the performance of the structures and also studying the history of the earthquake, at the same time the peak ground acceleration values also, later on zone 1 and zone 2 were combined together, and now presently, that is IS 1893 2016 is having this particular map where the entire country is divided into 4 zones, that is zone 2, zone 3, zone 4, and zone 5. So if you look at the map, the blue colored area is indicating the zone 2, the yellow colored area is indicating the zone 3, the green color area is indicating zone 4, and the pink color area is indicating the zone 5, right? The zone 2 is going to be the area which is going to be, you can say, least prone to earthquake, and zone 5 is the area which is going to be highly prone earthquake zone, right? So structures in this particular zone are going to have some special features which we don't have in zone 2 and zone 3. And if we talk about Gujarat, then you can see in the map that most of the Gujarat, that is 70% of the Gujarat, lies in seismic zone 3, and the rest of the zone lies in zone 4 and zone 5. Very minor belt, that is the green zone, you can see is in zone 4, and the remaining portion is in zone 5, right? So that is all about the seismic map. Now coming to the question of applications, that on what type of structures you need to consider the codal provisions mentioned by IS 1893, right? So that the code is clearly mentioning that the seismic parameters mentioned in this code shall be applicable to the following types of structures. First, buildings, whether it is ground story building or a 5-story building or a multi-story building or a high-rise building or a skyscraper. In all these cases, IS 456, IS 1893 is going to be the basic codes that you are going to refer. Then depending on the height, if there is an additional parameter, or depending upon the functionality of the building, if there is an additional code that is there, then in that case that code has also to be considered. That is, for example, if I am talking about tall structures, then in addition to IS 1893, you need to consider the clauses of IS 13920 also, and you also need to consider the clauses of tall structures, that is IS 16700 also. Right? Similarly, if I am talking about industrial structures, then IS 1893 part 4 is introduced specifically for special structures in industrial structures, where some of the features have been modified and the values of the parameters have been modified depending upon the functional requirement of the structure. Right? However, IS 1893 part 1 and IS 456 are going to be the basic codes that you need to consider for any type of structure that you are going to design. Second code is the second type of structure it is mentioned is the liquid retaining structure. Then third is embankment and retaining walls also can be included in this particular category. That is the retention of water as well as retention of earth, both are considered. Then bridges, any type of bridges shall also be considered for this particular type of codal provisions that are mentioned over here. Then industrial stack-like structures where silo, chimney, industrial plants, manufacturing units, all these are included. Then you have the concrete dams, masonry dams and the earthen dams. All types of dams are also included in this particular category. Then a very small structure such as security cabin should also be designed. So code is mentioning that security cabin, parking facilities, parking structures, these structures also need to be designed for these earthquake loads. And lastly, we have the nuclear power plants also, the petroleum refinery also, the special structures based on which you can say the performance or the economy of the country is dependent. These structures also need to be carefully designed for the codal provisions mentioned in this particular code. And lastly, it is mentioning that temporary structures like scaffolding and open excavation, these type of structures should also be considered for the earthquake loads, and the codal provisions mentioned in this particular code should be followed. Right? So this has given us a clear picture about what are the different types of structures wherein the codal provisions had to be considered. So basically, in a lump sum or a summary manner, I can tell that any structure that if you want that particular structure that you are constructing on the ground has to be designed for the earthquake loads mentioned in IS 1893. Right? Now, as we have seen the design philosophy, we have discussed regarding the three types of earthquake that the design philosophy is talking about. First is minor, second is moderate, third is strong. Similarly, we have certain assumptions also based on which the provisions are presented over here. Now, which are those provisions? The first provision is that the resonance in the structure shall not occur except for special cases. That is why, because the earthquake ground motions are going to be complex and irregular in nature. Right? Sometimes the intensity is more, sometimes the intensity is less, and depending upon the intensity and the magnitude, and also depending upon the location, the features of earthquake such as focal depth, the load path, the soil strata through which the soil is going to transfer, all these are going to affect the ground motion. And based on the ground motion, the ground acceleration is going to be transferred to the structure, and then the ground shaking is going to initiate in the structure itself. So as a result of that, what is happening is that this general assumption that is made is that the resonance will not take place because the amplitude cannot be controlled. Second assumption is that in case if we are considering a particular structure that is going to be designed for earthquake load, then along with the earthquake load, simultaneous application of any other type of lateral load is not permitted. That is, the lateral load due to wind, lateral load due to sea force, lateral load due to sea waves or floods or tsunami, or in that case cranes. Right? For example, we are talking about industrial structures, then in that case cranes are also there. That is because cranes are also going to introduce a horizontal thrust upon its start and in the stopping process. So the code is telling that whenever the earthquake forces are considered, then as a result of that, the simultaneous other lateral forces should not be considered. That is, you can have individual load combinations for earthquake, for wind, for crane, but a combination where earthquake is also there, crane is also there, or earthquake is also there and wind is also there, that is not permitted or suggested by the Indian standard over here. Some of the philosophy is also telling that you can take in terms of percentage if you want to be on the safer side or the conservative side. That is, you can consider one load combination where you are considering 30% as earthquake load and 70% as the wind load. Or the second case can be you are considering 30% as wind load and 70% as earthquake load. But that is going to be always on the conservative side. Code is not suggesting that you should take simultaneously two lateral loads at a time. And last is the values of modulus of elasticity for materials shall be taken as those obtained from static analysis only, unless and until specific experiments are conducted for dynamic conditions. right? So these are three basic assumptions that are discussed for the guidelines and the provisions that are mentioned over here in this particular code, that is IS 1893/2016 part 1. Next we come to the load combinations, because we are going to have primary load cases in the form of dead load, live load or the imposed load, and then we are going to have the earthquake load. Now in case of earthquake load, we all know that the earthquake is going to act in three directions, that is x direction, y direction and z direction. However, the effect of earthquake is going to be predominant in two horizontal directions, that is the x direction and the z direction, right? So what is going to happen is that the code is suggesting the load combinations if you are going to consider the simultaneous effect of earthquake in two principal directions at the same time. First of all, the code is telling that whenever the lateral load resisting frames are available in both the directions, earthquake load only in one direction should be applied at a time. That is, you have a good amount of moment resisting frames available in x direction, you have a moment resisting frame available in the y direction also, right? If both these systems or both these requirements, both these frames are present in the plan at the same time, then in that case only the earthquake load shall be applied only in one direction at a time. If the situation is that you have a moment resisting frame available only in x direction and you don't have a moment resisting frame available in the y direction, right? Then in that case the code is suggesting that you should take the components of x direction of earthquake also and y direction of earthquake also simultaneously. But how? It is telling that in that case, if you are going to consider the earthquake in two principal directions, then in one direction 100% load should be considered, in the second direction only 30% load should be considered. That is, for example, if you look at the load combinations, then the load combinations that we generally have based on the codal provisions that are mentioned in IS 456, then we have the load combinations for the general case as 1.2 times dead load plus live load plus earthquake load. This is going to happen when the moment resisting frame is available in both the directions. However, if you have a moment resisting frame available in only one direction, then this earthquake load is going to be replaced by two components, as you can see over here, that is ELX plus or minus 0.3 ELY, and the second time it is going to be ELY plus or minus 0.3 ELX, right? So when the moment resisting frames are not available in both the directions, then it is telling that you have to consider the earthquake in two principal directions, and at the same time the components of the factors that you have to consider that were also mentioned. Now other case may be such that where you are going to consider the earthquake in all the three principal directions acting at the same time. So in that case also the code is telling that in that case also you have to consider 100% in one direction, then in the second case you have to consider the other direction, and the 0.3 factor should be applied in that case also, as you can see over here, right? So the general load combinations are 1.2 times dead load plus imposed load plus earthquake load, second 1.5 dead load plus earthquake load, and lastly 0.9 dead load plus 1.5 earthquake load. So all these combinations will be modified depending upon the structural geometry that you are going to have in your structural configuration or the structural system that you are working on, and based on that the load combinations need to be modified in the STAAD model or the ETABS model that you are considering. Right. Next we talk about the vertical earthquake effects. Now if you refer IS 1893/2002 part 1, then in that case the effect of vertical earthquake was not clearly mentioned. That is, it was mentioned that only if the structure is going to have some kind of overhangs, that is the cantilever portion or the horizontal projections, then only it was mentioned that it, on the conservative side, it is better to consider the vertical earthquake effect also there. But however, now in this revised course, that is IS 1893/2016, the vertical effects or consideration of vertical earthquake have been mentioned explicitly. Earlier in the 2002 version it was implicit, now in the 2016 version it is mentioned explicitly, and for that 6 conditions are mentioned. Now which are those 6 conditions where I need to compulsory consider the vertical earthquake also? That is, first is that if the building or the structure is located in zone 4 or 5, that is, if the building is located in high seismic zone areas, then in that case vertical earthquake has to be considered. Second, that if the structure is having a plan irregularity or the vertical irregularity, that we are going to discuss in the session ahead. Then if the structure is located on soft soil, that is, if the N value of the soil is less than 10, then in those type of structures also vertical earthquake effect has to be considered. Then for bridges, it is considered that for any type of bridges the vertical effect should be considered. Then that if the structure is having large span, then in that case also it is advisable that the vertical effect of earthquake should be considered. And lastly, the one that was mentioned in the earlier revision, that was 2002, that is, If the structure is having large horizontal overhangs or cantilever projections, then in that case also the vertical effect should be considered. That is, in addition to the calculation of horizontal acceleration spectrum, you need to calculate the vertical acceleration spectrum also. How to calculate horizontal acceleration spectrum and vertical acceleration spectrum, that we are going to discuss in the lecture ahead. Right. So now there is one another characteristic or one another feature that the code IS 1893 to 1893 is discussing, and that is the increase in the net pressure of the soil for the foundation designs. That is, the code is telling that whenever you are going to design particular structure for the earthquake, then in that case you can have some increase in the stresses, or you can have the increase in the soil bearing pressure if in the following three categories, where it is mentioned that type A soil, type B soil and type C soil. Now type A soil is the one which is known as the rocky strata or the hard strata. Type B is the medium strata and type C is the soft strata. Now in case of the rocky strata, the permissible increase in the bearing pressure can be increased by 50%. Second, in case of medium strata, it can be increased by 25%. And lastly, in the soft strata, it can be not increased. Right? So now what is happening is that where is the application of this particular thing? That has to be understood. Right? For example, if I take the example of an isolated footing design where I am having the load, and based on the load I need to find out the area permissible or the area required. Then what I will do is load divided by SBC will give me the area required. Right? So what the code is telling that if you are considering the load for the gravity cases, that is dead plus live, then no increase in the value of SBC has to be taken. For example, my SBC is 100 and my load is 800. Then area required is equal to 800 by 100, that is equal to 8 meters square. However, if I am having the second load combinations where the effect of earthquake is present, that is dead load plus earthquake or dead load, live load plus earthquake, then in that cases, in all these unfactored load cases that have to be kept in mind. That is, in all these unfactored load cases, I can increase the value of SBC. That is, I can increase the value of SBC based on the soil strata as per the values given in table number 2. That is, for example, I am having a medium soil. Then in that case, for the second load combinations, area required will be equal to 800 divided by 100 into 1.25. Right? So wherever the earthquake load combination will be there, an unfactored load combination will be there. There in that case, in order to take the advantage in terms of sizing of the foundation, you can increase the value of bearing pressure. But this advantage is not available in case of soft soil. Why it is not available? Because when soft soil is going to be there, and as a result of that, excessive settlement is likely to take place. And by increasing the pressure, the settlement cannot be controlled. Right? So as a result of that, the code is telling that in case of soft soil, the increase cannot be taken. Now, what is the definition of this hard soil, medium soil and soft soil that the code is mentioning? So for that, the guideline is given in table number 1. That is, for example, I am talking about the hard soil or the rocky soil. Then in that case, it is mentioning that soils having the classification as SW or GW, that is well graded sand or well graded gravel, and having a n value greater than 30. This is an important parameter that we should take consider. That is, if the n value is greater than 30, then that particular type of soil can be considered as hard soil or rocky soil. Then the second category is the medium soil, where the soil is going to be stiff to medium in nature, and the n value is going to be in the range of 10 to 30. And if I take the examples, then I can take that the soil classification SP, then the other GP, or I can take the classification as CI. These type of CL, these type of soils are going to fall under the category of the second case, that is the medium soil. And lastly is the soft soil, where the n value is going to be less than 10, and it is going to be of very soft nature, that is excessive settlement is likely to take place. And if I take the examples, then it is MH, ML, CL, CH, that is the soils of low compressibility and soils of high compressibility or intermediate compressibility will fall under the category of soft soil. And last is the collapsible soils. Collapsible soils are those soils where the danger of liquefaction is possible under the effect of lateral loads. So in that particular case, the structure should not be founded on that particular type of soil without the ground improvement technique has been adopted. Wherever the liquefaction potential is there, then any of the ground improvement technique should be adopted, and after achieving certain amount of shear strength, then only the structure should be constructed on that side after due consultation with the geotechnical consultant. Right. Next, we talk about the design acceleration spectrum. So I have mentioned that design acceleration spectrum is divided into two categories. First is the horizontal spectral acceleration, and second is the vertical spectral acceleration. Right. So Here the formula that is given is for the horizontal, that is it is indicated by AH and it is given by ZISA by 2RG, where Z is the zone factor, I is the importance factor, R is the response reduction factor, and SA by G is the design acceleration coefficient. Now zone factor, as you can see in the earlier in the next slides also, where the depending upon the zone, that is zone 2, zone 3, zone 4 and zone 5, the value of Z is defined by the code. If I talk about importance factor I, then it is based on the importance of the building and the utility of the building. And in general, the code is telling that for residential buildings or general buildings, the value of I should be taken as 1. For business buildings or commercial buildings, the value of I should be taken as 1.2. And for special structures such as power plants or nuclear power plants or petroleum refinery, this value should be taken as 1.5. Right? And lastly, we have the response reduction factor, where the response reduction factor is given in the tabular form based on the structural configuration that you are having. For example, whether you are having moment resisting frame, special moment resisting frame, or you are having a dual system, or you are having a structural system where only the shear walls are present, or flat slab system is there, or concentric braces are there. So depending upon the type of configuration that you are having in the structural system, the value of R has to be selected from table number 4 of IS 1893. And lastly, we have SA by G, that is the design spectral coefficient, which will be corresponding to the peak ground acceleration corresponding to the different types of soil, right? And this peak ground acceleration, as we know, is dependent upon the time period of the structure. So for the time period of the structure, again you can see that a tabular format is given, where for static analysis and dynamic analysis, both type of analysis, the value of SA by G have been given differently. Earlier, in the earlier revisions 2002, we had only one table, but now for this particular, that is IS 2016, two different tables are given for static analysis as well as dynamic analysis. So if I look at the table of static analysis, then as I can see that for SA by G value, 3 categories are given. That is the hard soil, medium soil and the soft soil. And corresponding to the 3 types of soils, the value of SA by G is given corresponding to different time periods. For example, in the first category, the limit is given as for a time period in the range of 0 to 0.4, then 0.4 to 2.55, or 0.4 to 4 seconds, and time period greater than 4 seconds. So if the value is going to be Z such that, then the value of SA by G in general is 2.5, 1 by T, and accordingly. Second case is the medium category of soil, where the range of time period is given in the range of 0 to 0.55, 0.55 to 4 seconds, and greater than 4 seconds. And lastly, if I talk about the soft soil, then 0 to 0.67, 0.67 to 4 seconds, and greater than 4 seconds. For all these 3 different categories and different time periods, the value of SA by G is given over here. And similarly, in case of dynamic analysis also given, but you can see that in case of dynamic analysis, the difference is going to be in the range of time period. In case of the static analysis, the range is starting from 0.4. Whereas in case of dynamic analysis, the value of time period is starting from the range of 0.10 only, right? So that is another difference between the considerations for static analysis and the dynamic analysis. And lastly, we look at the values of zone factor that are mentioned by IS 1893-2016 depending upon the location of site that is mentioned in the seismic zone map of India. That is, for zone 2, the value is 0.10, zone 3, the value is 0.16, zone 4, the value is 0.24, and zone 5, the value is 0.36. So the value of AH is equal to ZISA by 2RG, where Z is the zone factor. So that value of zone Z is to be taken from the table 3 that is mentioned over here in IS 1893-2016. I hope the discussion that we have had today has given you a clear indication about the importance of IS 1893, the application of IS 1893, and the assumptions and certain basic considerations for the clauses that are discussed for the application of earthquake load on any type of structure. Stay tuned for the further lecture series. Thank you.